Ever find yourself scrolling through a social media feed,
Yeah.
with millions of users?
Mm.
I wonder how they manage to pull up your friend's post in like a split second.
Hmm.
Or how a stock trading platform can execute trades,
Huh.
you know,
Right.
in milliseconds.
Right.
Mm-hmm.
Today's deep dive is all about the secret sauce that makes that kind of speed possible. Constant time operations in Java, or O1 for short.
Yeah.
We've got your cheat sheet right here, ready to break down this core concept that's like a superpower for making programs run lightning fast.
That's right. It's about understanding how to make code incredibly efficient.
Yeah.
Whether you're like a coding whiz or just curious about how software works, Grafting O1 can give you a whole new appreciation for the magic happening behind the scenes of the technology we use every day.
Okay. So I'm already intrigued. Where do we even begin with this whole O1 thing?
The best way to visualize it is with a simple analogy.
Yeah.
Like flipping a light switch. It takes the same amount of time to flip that switch, whether you're in a tiny closet or a massive stadium.
The size of the input, in this case, the room, doesn't affect how long the operation takes.
So it's like a fixed amount of time.
Yeah.
No matter what.
Precisely. And in programming, that's exactly what a constant time operation means. The speed of the operation is independent of the amount of data being processed.
Yeah. If you're dealing with a gigantic data set, like all the user data on a social media platform, using an O1 operation would mean it wouldn't slow down even as the data grows.
That's why it's so crucial for creating efficient and scalable code. If an operation's speed is dependent on the size of the data, your program can grind to a halt when you're dealing with massive amounts of information.
Right, like those times you're waiting forever for a website to load or a game to render graphics. Not fun. So O1 is all about avoiding those bottlenecks.
Absolutely. Think about those time-sensitive applications we mentioned earlier, like stock trading platforms or real-time game graphics. Every millisecond counts. In those scenarios, relying on constant time operations is essential for smooth, responsive performance.
Okay, so I'm starting to see why this is a big deal. Now, our cheat sheet here lays out 6 examples of O1 operations in Java. Ready to dive in and break them down?
Let's do it.
All right. Example number 1. Accessing an array element, Einco. The source material uses a great analogy here. Imagine a row of numbered boxes. You know exactly which box you want. That's like having the box's index. It takes the same amount of time to open box number 3, whether there are 5 boxes or 5 million.
It's all about that direct access. You don't need to search through the entire array to find the element you need. The index tells you exactly where it is, making it an O1 operation.
It's like having a map with a specific address. No need to wander around searching.
Exactly. Now, let's move on to example number 2, assigning a value to a variable. Think of this as putting a label on a box, super quick, and it doesn't matter what's inside the box.
So it's a simple action, like labeling something.
Yeah.
That happens in a fixed amount of time, regardless of what you're labeling.
Precisely. It's a fundamental operation that, despite its simplicity, is a building block for efficient code.
Interesting. Okay. What's next on our list?
Example number 3, adding an element to an array list. This one is a bit more nuanced, usually. It's as straightforward as adding a new car to the end of a train. Nice and easy.
Okay. So far, so good. But you said usually. Does that mean there are exceptions?
You're catching on. Sometimes you need to make the train longer, which in programming terms means resizing the array list. And that, my friend, can take a bit more time.
Hold on. So it's not always a strict O1 operation then?
You're right to point that out. If the array list needs to resize itself to accommodate the new element, it could take a bit longer. However, on average, adding elements to an array list is still considered an O1 operation.
Okay. So it's usually a quick operation, but there are those occasional hiccups where it might take a bit longer. This highlights how even with seemingly simple actions, there are hidden complexities.
Exactly. And that's why understanding the nuances is so important. Now, you're ready for example number 4.
Hit me with it.
All right. This one is hash map key lookup.
Imagine a super organized library. You have the book's Dewey Decimal number, that's the key, and you can go straight to the shelf where it belongs. No searching through every single book in the library.
So it's like having a magical librarian who instantly knows where every book is located.
That's a great way to put it. Hash maps use a clever trick called a hash function to achieve this direct lookup.
Okay. I'm a bit fuzzy on what a hash function actually is, but it sounds like it's doing some heavy lifting to make this instant lookup possible. Can you break that down a bit more?
Of course. Imagine it like this. Each book is assigned a special code based on its title. This code acts like a secret address that tells us exactly where on the shelf to find that specific book,
Mhm.
no matter how many other books are in the library.
So it's like each book having a unique GPS coordinate that leads you straight to it. Exactly. That's the power of a hash function. It converts the key, in this case, the book's title, into a unique index that directly points to the location of the data. This eliminates the need for any searching, making the lookup incredibly fast and efficient.
Wow. So we're essentially trading a bit of memory
Mm.
to store all those codes
There.
for a massive speed boost.
Mm-hmm.
That's a pretty clever trade-off.
Yeah.
Okay, what else is on our O1 list?
Next up, we have checking membership in a hash set. Example number 5. This time, picture a VIP list for a party. Checking if someone's name is on that list is super fast because it's organized specifically for that purpose.
So it's similar to a hash map where the way it's structured makes it O1. No need to scan through the entire list. You just go straight to the name you're looking for.
Precisely. Both hash maps and hash sets leverage their organizational power to enable those constant time operations. And finally, we arrive at example number 6, modular arithmetic.
Okay, this one sounds a bit more technical. What's the gist of it?
Think of it as finding the remainder after a division. No matter how big the numbers are, the calculation itself is always swift.
So it's like a mathematical shortcut that always takes the same amount of time.
Yeah.
But why would we need that in programming?
Great question. While it might seem like a basic operation, modular arithmetic is actually used in a ton of important applications. For instance, cryptography, which helps keep your online data safe, relies heavily on this concept.
Whoa. I never realized something as seemingly simple as finding a remainder could have such a huge impact on security. So we've covered all 6 examples of O1 operations in Java, but how does this all translate to real-world software beyond just making things a bit faster?
That's where things get really interesting. It's not just about speed, it's about scalability. Imagine you're designing a social media platform with millions of users, each with tons of data, posts, photos, friends, the whole 9 yards.
Right, it's like this massive,
Yeah.
interconnected web of information.
Exactly. Now, let's say you want to add a feature where users can see who's viewed their profile. If you use an inefficient algorithm that slows down as the number of users grows, that feature will become unusable as your user base expands.
So it's like those growing pains you see with some websites or apps. They work fine when they're small, but then they get super slow and clunky as they get more popular.
You got it. But if you design the feature using O1 operations, like accessing elements in a hash map or checking membership in a hash set, you can ensure it stays fast and responsive no matter how many users join the platform.
So it's like future-proofing your software by making sure it can handle tons of data without breaking a sweat.
Exactly. And that's why understanding O1 is so crucial, especially for developers working on large-scale applications. It's about building systems that can scale and adapt to the ever-growing demands of the digital world.
I see. It's not just about making code run a few milliseconds faster.
Yeah.
It's about creating systems that can actually keep up with the massive amounts of data we generate every day. So for all the aspiring coders out there, what's the key takeaway here?
The key takeaway is this. As you're learning to code, think about the efficiency of your algorithms from the start. Look for opportunities to use O1 operations whenever possible. Not only will this make your code faster, but it will also make it more robust and able to handle whatever challenges come its way.
So it's not just a cool trick. It's actually a fundamental principle for building good software.
But what about those of us who aren't planning to become programmers? Is there anything we can glean from this deep dive?
Absolutely. Think about it like this. Have you ever been stuck in a long, slow line, whether it's at the grocery store, the DMV, or a concert? We've all experienced those frustrating bottlenecks.
Oh, tell me about it. Sometimes it feels like those lines are designed to test your patience. But what does that have to do with O1?
Well, think about what causes those bottlenecks. It's often a process that isn't optimized for efficiency. Maybe there aren't enough checkout lanes open, or the paperwork system is convoluted and slow. Recognizing these bottlenecks in any process, whether it's in code or in real life, is the first step to improving them. So it's like taking that programmer mindset of looking for efficiencies and applying it to everyday situations.
Exactly. Just like a programmer might analyze their code to find and eliminate slow operations. We can analyze the processes we encounter in our daily lives and look for ways to make them more efficient.
So instead of just grumbling about a slow line, we can actually think critically about why it's slow and whether there's a way to streamline it. I like that.
And who knows, maybe you'll even come up with a brilliant solution that makes everyone's life a little bit easier.
Now that's a challenge I can get behind. So we've gone from light switches to libraries to lines at the DMV, all thanks to this idea of O1. It's amazing how these seemingly abstract concepts can actually have such a wide-reaching impact. It really makes you appreciate all the clever work that goes into making the technology we use every day feel so seamless.
It's like an invisible symphony of efficient operations happening behind the scenes. And,
Right.
understanding those basic principles of efficiency, like
Yeah.
O1, gives you a whole new level of appreciation for how it all works.
Okay, so before we wrap up this deep dive, I want to circle back to something you mentioned earlier, Big O notation. You said it's like the ultimate guide to understanding the efficiency of algorithms. And it sounds like it's closely related to this whole O1 thing.
It absolutely is. Think of Big O notation as the language we use to describe how the performance of an algorithm scales with the size of the input. O1 is just one type of Big O notation,
Yeah.
representing those constant time operations we've been talking about.
There are other types of Big O notations for operations that aren't constant time.
Exactly. There are notations like ON, where the time it takes scales linearly with the input size, and ON2, where it scales even more dramatically. Understanding these different notations helps programmers choose the most efficient algorithms for a given task.
Ah, so it's like having a toolbox full of different efficiency options and knowing which tool to use for which job.
That's a great analogy. And just like a skilled craftsperson chooses the right tool for the task at hand, a programmer who understands bigger notation can select the most efficient algorithm to build fast, scalable, and reliable software.
This is making me realize there's a whole world of fascinating stuff going on behind the scenes of even the simplest apps and programs.
And it all comes down to understanding those fundamental principles of computer science. It's like cracking a secret code that unlocks a deeper understanding of the digital world around us.
Well, folks, I think we've officially decoded the mystery of constant time operations and dipped our toes into the vast ocean of Big O notation. From light switches to libraries to long lines, we've explored how this concept of O1 can apply to code and to life in general.
And remember, this is just the beginning of the journey. If you're feeling inspired to learn more, there's a wealth of resources out there waiting to be explored.
Exactly. And who knows, maybe this deep dive has sparked a newfound curiosity in you about the world of programming or the power of algorithms.
Perhaps you'll even start noticing those bottlenecks in everyday life and come up with your own innovative solutions to make things more efficient.
So to wrap up today's deep dive, I want to leave you with a challenge. Think about the tasks you do every day, both at work and in your personal life. Are there any processes that feel clunky, slow, or just plain inefficient?
Could you apply some of the principles we've discussed today? Like eliminating unnecessary steps, finding shortcuts, or organizing information more effectively to make those processes run more smoothly.
We challenge you to put on your programmer hat, even if just for a moment, and see if you can spot those opportunities for optimization.
And who knows, maybe you'll uncover some hidden efficiencies that make your life a little bit easier and a little bit faster.
That's it for today's Deep Dive, everyone. Thanks for joining us on this journey into the fascinating world of efficient code and the power of constant time operations.
Until next time, keep those minds curious and those algorithms optimized.